Okay, so I'm going to cover a bit of a very big topic. This is a huge area. I'm going to draw out a few use cases which I think are important at the moment and talk about the technologies behind it. These slides are available. The link at the bottom there is you can get the full deck of the PDF. So this field is massive, and right now it's been growing for about 5 years exponentially. The number of papers being submitted at conferences are at all-time high, and there's loads of different areas going on here. So we can't really cover it all in the time available. These are the kind of 9 areas that I think are quite important at the moment. And the impact of deep learning on these areas is quite significant. There's more to vision than just deep learning, but right now that's a lot of the state-of-the-art solutions are based around deep learning. We're not going to cover it all today. We're going to look a lot at the stuff on the top row, so kind of extracting information from pictures and video. I've got a case study on 3D reconstruction, looking at teeth scanning, and also we'll have a quick look at synthesis, so generating new data. And in fact, that was my next slide. Okay, so let's start with just a bit of introduction and background. So this is me. I'm a consultant at TTP. We're a Cambridge-based consultancy. About 300 scientists, engineers, and we do things like medical, industrial, defense, clinical systems, healthcare, all kinds of building new products. And AI is a part of that for us. So some of my work includes, obviously, looking at teeth, looking at myself. This is my PhD, looking at cell sorting for life sciences. And at the top there is a video analytics piece we did a little while ago. And okay, so when we started this kind of deck, I wanted to draw out some of the major events because it's a big area. So I started with 2 timelines, one for vision, one for AI. But actually, I mean, the overlap is big. And do you put CNNs in AI, or is it a vision thing? I mean, who knows? The thing with AI, I guess, it comes in peaks and troughs. And right now, it's on a peak. It's not like that always. It was on a peak in the 90s and in the 70s, but a lot of the stuff we're doing right now is all based around deep learning and understanding the content. A couple of key things here, I guess. In like the late 90s, we had SIFT. That algorithm has been used in everything from merging pictures to 3D reconstruction. It's a huge piece of work. 2009, Microsoft Kinect. Do you remember that? It's like a camera you mount onto a games console. That actually holds the record as the fastest selling piece of consumer hardware in the world. They sold 133,000 units a day for 2 months. We've got Snapchat filters. So right now, there's a lot happening with vision, and it's just a big market. Let's start looking at object detection and segmentation. So when we have a picture, there's a lot of data in that picture. It contains millions of pixels, and often we want to be able to get a bit more out of that than just a very large matrix. So 3 ways we might approach that are classification, detection, and segmentation. And that comes down to how much information you want out the other end. So here we've got some fish. If you just want to know what the content is, you can classify it. And that'll tell you that that's a fish with a 0.84 probability. If you want to know where the fish are, you might run detection algorithms, and that'll give you a bounding box. It'll draw the box around the outside. Finally, if you want to know exactly where the fish are to a single pixel, you might use segmentation. But obviously, the output from that is a lot more complicated than the output from a classifier. So let's just start at looking at a few of those. This deck contains lots of pictures of me. It's not just because I'm out of vein, it's just it's quite handy. So this is running me in a mug through a classifier. At the top, you've got the label, so the highest scoring category that the classifier thinks that belongs to. And the kind of things you can categorize are by the content in images, so cats and dogs, or different types of car, for example. You can also classify on the image characteristics. Is it blurry? Is it not? Is it black and white or color? And as you can see, it doesn't always get it right. So here we're taking the highest scoring label. Now you can see from the values next to it, those are the confidences. That is how strongly the classifier believes that this picture here is of a burrito, or of a fridge, or of a neck brace. So whereas the coffee mug, it has high confidence, so 0.733. These numbers are between 0 and 1. So 1 represents complete confidence, 0 is not confident. So why is this getting it wrong sometimes? Well, what we're doing here is looking for patterns in the image, so things that could be indicative of something else. You can probably see why you might say that a square white shape looks like a fridge, or why a person with a white object by their neck could be a neck brace. I'm not sure about the burrito, though. That's something else. So what are we doing here? Well, the current state of the art is a deep convolutional neural network. So this is a type of neural network where we use convolutional layers, and we pass in an image at one side, and at the other end we get a classification, which is a confidence that that image belongs in each of, in this case, 10 classes. Can I just get a quick kind of from the room, how happy are we with deep learning and CNNs? Is this understood? Maybe? Not at all? Okay, we know a bit about it. So I'm not going to dwell here too long. But what we're doing at each of these layers is we're doing a mathematical operation. So we're running an operation on the input to that layer. Have the whole slide if you want. So in the case of convolution, we have what we call a set of kernels, which these are patterns we're looking for in the data. And we calculate the convolution between that kernel and patches of the image. And the size of that convolution, so how much that pattern is expressed in the image, is reflected in the output. So what we're doing here really is we have a stack of feature extractors that look for parts in the image that it recognizes. At the very far left, in the first convolutional layer, we've got kernels that look for small features, things like corners, edges, textures, quite important. And as we progress through the network, we're then looking for groups of features. So if you have lots of edges, you get a line. Lots of curves, you get a circle. And further through the network, we're starting to build up this understanding that, well, I can see groups of circles or groups of shapes I recognize. And then at the end, we have a classifier that says, well, I've seen this many things I recognize, and this looks to me like a cat or a dog or a car. Okay, so that's classification. And in that case, we just get out what category the image is from. Quite often, we want more than that, though. We want to understand a bit more about the image content. And especially if you've got an image with a mixture of objects in there. So in this case, we've got a plant, we've got a mug, we've got me, we've got a laptop. And this is an object detection algorithm called YOLO, which stands for You Only Look Once. This is one of a range of different algorithms. This one's optimized for speed. So you put the image in, and in a single pass of the network, you get the detection of the boxes. So really what we're doing here is running a classifier on parts of the image. And if you imagine a grid running across the image, and you classify the contents in each box, and then merge that result together to give you an estimation of the size of the object. So, for example, my face and body crosses the middle third of that grid. And we've probably classified for example, 9 different regions in the area, and they've all returned person. So we know there's a large person in the front. Now, this kind of approach, it's very quick because you can process a whole image in a single pass. However, it's less accurate. Let's look at a different example doing the same kind of thing. So this is a street scene. And here we've got a classifier that knows about cars, about buses, about cyclists, and also people. So this is a slightly different example. This is a combination. It's a classifier and a region proposal network. So we have a network that looks at the image and identifies things that could be objects. And then those objects are passed to a classifier to say what they are and how confident are we what they are. What we might have seen before was that, for example, when the bus drove in front of the car, we lost track of what was behind it. And that's entirely reasonable. If you can't see the car, why would you say it's there? However, there's cases when we would like to be able to do that, to track objects between frames and to say, I saw that car earlier, or that person. And so we can take it a step further by tracking objects between frames. So in this case, we run the same kind of algorithm where we detect objects in the image, but then we look at the trajectory of that object. So which directions are moving in, and also what does it look like? So this is very similar to the way that humans look at things. We look at an object and recognize based on, for example, the clothes you're wearing or the color of your hair. And in this case, we use a neural network to identify visual features. Now, these aren't as discrete as the color of your hair or the clothes. They're called latent features. But we process the image and get out a latent vector, which contains features that the network believes are important to describe that object. So let's look at how that works. Here we've got a crowded street scene, and we're looking for just persons, just people. This is an algorithm called Deep Sort from 2017, and each time it detects a person, it looks at the way that person's moving and also their visual features. And then in the next frame, it looks at what could be where we would expect that object to be now. And if it is in that place and looks the same, it's probably the same person. So that lets us keep track of objects between frames, even if they move out of view for a period of time. Okay, let's go a step further. So rather than just looking for objects, we want to know what they're doing. And rather than just knowing the coordinates of a box around that object, we want to say, for example, it's a person, where are their arms and legs. So this is a pose estimation example from OpenPose, produced at Carnegie Mellon University. And for each person in the image, it extracts key points. So you get the shoulders, the elbows, the hands. If you want, you can even go as far as processing the joints in the fingers. And once you have that data, then you can start to ask questions like, given the movement of that person, what are they doing? This is an example of how it works in reality. So for each frame of video, we calculate the pose. That gives us a long list of numbers, which is the coordinates of each point in their body. It's still a lot of information, but it's much less than you get in the whole video stream. And so then you can run a classifier across that sequence of information and say, that looks like the person is running, they're walking, they're climbing, they're fighting. Certainly in the case of security, that lets us do more with the data we have, because just having a raw video stream requires a person to sit there and watch it and say what's going on. If you've got 10 cameras, more, it's even harder. You have 10 screens. It's very hard for one person to monitor video constantly. By running this kind of algorithm over the top of that, you can then start to flag up events to the user. Say, on camera 10, there's a person who's acting differently to everyone else. What does that mean? And that's a way to get a bit more value out of the information. Okay, let's go even further. And rather than looking for boxes or for key points, we want to know for every single pixel in the image what it is. This is where segmentation comes in. So this network is called a UNet, and that comes from the shape. What we have here is a stack of convolutional layers, like we saw earlier for the classifier. But in this case, at each stage, we downsample the image until we get to this latent space in the bottom, which is a very reduced dimensions data. And then we upsample the image. So we output, rather than a single value that says it's a cat, it's a dog, or rather than a box which says the coordinates are here to here, we get a map that represents, for every pixel in the image, what we believe the class of the image is. Now, that's a very rich source of information. And one area that's used is in autonomous driving. So there's two approaches, really, to understanding street scenes which are widely used. One's using a camera and segmentation, and the other is with LiDAR. So in this case, we have a standard camera, like a forward-facing camera. And the output is run through a neural network. And what you get out is, for every frame of video, this map of what's in the area around you. And you can see here we've segmented people, cars, street furniture, and roads. This has the advantage that you can use it on normal hardware. You have a normal camera. The difficulty is that you need a lot of labeled data for this. So these algorithms are trained using supervised learning, which means that you need to have both the image and also the labeled data. And the way that works currently is somebody sits down and labels this image by hand, so draws the lines around these images. And for a typical skilled worker, that can take half an hour per image. But many companies have gone out there and labeled large volumes of this data. There are data sets you can buy with tens of thousands of these images in. The alternative is to use LiDAR. So this is using a laser beam to measure the distance to the surrounding objects. This is the example from Waymo, so the Google offering. You can see on top there's this kind of thing that looks like a beacon on top of the car. That's the LiDAR. That's a spinning mirror that shines a laser beam in all different directions and measures the distance from the sensor to the object. What you get out is called a point cloud, which is like this image at the top. And the laser hits an object, it reflects back, you measure the distance. And so you can see in the field where it's hit an object, there's a shadow behind it. And that's because the light doesn't reach behind the object. Now, this has the advantage of range. It's very long range. What you get out is a cloud of points in 3D space that represent the distance to the objects around it. So if you want to understand the information, you can either process the point clouds directly, which is very doable, although it's quite difficult because you lose information on texture. So you've got this map that shows you how far away things are, and you can extract from that the shape of objects. But what you lose is things like color and texture. So one alternative is to combine the data from the LiDAR with a normal camera, and then you can use a combination of approaches to do that. And that's quite powerful as well. Okay, let's move on from driving to 3D reconstruction. So, in fact, let's look at a case study. Okay, so this is an example of constructing a 3D model from a single or multiple 2D pictures. And I'm going to talk about an example which I've worked on, which is an intraoral scanner. So we'll look at how you go from an image through to a point cloud, through to a 3D model. But let's start with some stuff on stereo imaging. So having two eyes is essential for depth perception. And if you look around us in animals, most animals have reached a compromise between the size of their field of view and the region of field of view where they have depth perception. So in the case of a predator, they tend to optimize having good vision in front of them, so the eyes on the front of the face, and the field where their vision overlaps is quite large. So that gives them a large field of view in front of them with less perception out to the sides. Alternatively, some animals mount their eyes on the side of the head. This gives a very large field of view. It means that the region where they can see depth is actually quite small. And in this case, for the macaw, it's just for the very front, maybe 20 degrees. So that overlap for them is important for flying, because knowing how far away things are is quite key for flying. But it gives them a very wide field of view around the outside to spot, I guess, approaching predators. Now, in terms of 3D reconstruction, what we're looking at here is stereo. So we've got two cameras pointed at an object. And for each camera, we have a view of the scene. And if we look at a single point, so in this case the target, the position of that point in the two images is indicative of the distance from camera to the object. And by looking at the two views and finding out where that point is, we can determine its coordinates in 3D space. So what we look at here is kind of a simplified model where we're treating the cameras as points in space. This is called the pinhole camera model. In reality, the camera has lenses and optics, but by approximating it as a point in space, the maths becomes much easier. And we know that given the geometry, as that point moves towards or away from the camera, those 2 points on the images will move along a line. And that's quite important for calculating where it is. Okay, just as a little diversion, this is ways to represent objects inside a computer. So one way is a point cloud at the top left. This is a set of single points, just floating, well, not floating, just in space. There's no connections. Each point is defined by a coordinate, generally the x, y, and z. And together, it makes an object. On the right is a mesh formation, which is very similar, except for we've established links between points. And obviously that can be very coarse at the bottom or very fine at the top. But by having a mesh, you can then apply color and texture to it. Alternatively, if you wanted to, you can represent it as a set of cubes. Here we have a tree structure where we have large and small cubes. And this lets us represent objects in 3D space without using up lots of memory. Okay, so let's look at this case study. So when you go to the dentist, normally they'll look in your mouth with maybe a mirror as well to look at the health of your teeth. Also, nowadays, we're seeing a move towards using a scanner to put a model of the teeth. So rather than using perhaps a mold and some clay, here the dentist is using an intraoral scanner, which is a device with a pair of cameras on the end at different angles, and those images are used to create a 3D model of the teeth. And one application for this is to create orthodontic aligners, so like Invisalign. These are clear braces that are used to straighten teeth. This is the kind of thing we'd like to produce at the end, so a 3D model of the teeth and the surrounding gum area. You can see here that it's a thin section, so it's just the outside surface. And this is a stone arch with, you can see there's a couple of spheres on the top. These are used to calibrate. So this is like a fake arch made of stone. We scan the arch with the scanner and then measure the distance between the known points on those spheres. So how do we get there? We start off with 2 images from the camera, left and right, and you can see that they're very similar, but slightly different. That's because each camera has a slightly different view on the scene. And what we're looking for is points which are in both images, and then we want to know where they are. So what we do is use a matching algorithm that looks at blocks of the image and compares left and right. And what we're doing is looking for parts of the image that look the same in both images, and then working out where they're positioned. Now, actually, we know from the geometry that the point we're looking for will lie on a horizontal line. Because of the orientation of the cameras and the geometry, the point will move left and right, but it won't move up and down. So that makes things a lot simpler for the maths. And if we do that across the image, we do something called the normalized cross-correlation. We can then calculate a depth map, which looks a lot like this. So this is an algorithm called SemiGlobal block matching, and what you get out is a map across the image. In this case, the color represents the distance from the camera, and that provides you with the shape of the object. But it's all with reference to the coordinate frame of the camera. So if you move the camera around, the object changes. Next step is to convert that into a point cloud. So this is moving from the continuous shape of the depth map into discrete points. And again, this is still with reference to the camera. So here we have the x and y in the image, and z is the distance from the camera lens. And we pass lots of these point clouds through an algorithm to create a 3D model. So we can do it in 2 ways, either by looking at the image itself and looking for features that match between images, or we can do it by looking at the geometry. So each time we move the camera, we get a slightly different point cloud. And by comparing the shapes of those point clouds, we can create a larger model based on that overlap. Okay, let's move on to our last topic today, which is on image synthesis. So this is all about generating data, generating images. And it's an area that's been quite a hot topic for the last couple of years. A lot of it is down to these generative adversarial networks, which is a type of neural network that's been shown to be very useful for creating data. What we actually have is 2 networks that are trained in parallel. So the generator takes a random input and maps that to an image. And when you first use this network, it knows nothing about what it's meant to create. So you feed in noise and you get noise out at the other end. Then we have the discriminator. And the discriminator's job, it's essentially a classifier. And its job is to classify that image as being real or synthetic. And what we're doing is we're feeding it images from the generator, which are synthetic, and also we're feeding it real data, so in this case, a real face. And each time we run an image through the discriminator, it produces an output that says real or fake. But also it provides feedback to the generator to say which parts of the image it thinks are most real or most fake. So one way to think about this is an example I heard recently. Say you were trying to get into a concert or a gig, and you didn't have a ticket, but you had a blank piece of paper. And you take that paper to the doorman, and you show it to the doorman and say, I want to come in. And he says, no, you can't. That's a fake ticket. but then they tell you which parts of your ticket look the most fake. And then you go away, you change the ticket, and you come back and try again. And again, the doorman says, no, that's a fake ticket. But they tell you, again, which parts of your ticket look the best and the worst. And by going around that loop again and again and again, the generator learns to produce good images that look real. But at the same time, the discriminator learns to tell real from fake as well. And so these two networks progress in parallel. Eventually, it's a point where they can no longer get any better because they don't understand the content enough. But what we've seen is that the results that come out are very realistic. So this is an example called Stargun, which was published at the start of the year. And all of these pictures here are synthetic. So they're not real people. The network was trained on 70,000 real pictures. And now, each time you run it, it can produce a new set of synthetic images. And this was quite remarkable because the quality is extremely high. Now, to put this into context, this took a while to train, so it took a week on a workstation that costs $100,000. So it's quite expensive to train. But the quality of the output is very large, it's very high, and it's quite significant because it produces very large images as well. Here's another example. So the same technique used to generate images of cars. Now, none of these cars exist. And most of them, if you look closely, are kind of combinations of different types of vehicles. So wheels from one car and the bumper from a different car. You do occasionally get some unusual outputs. So, for example, the image at the top left has an incredibly large rear section, or the image on the right has kind of two bonnets, and the door at the back has two handles. But to a quick look, at least, it's quite it's quite powerful. So this kind of technique is quite useful if you need to generate new data. Now, generally, if you're working with real data, for say a classifier, often your data set is not very balanced. So you'll have some cases that are very common, and then a whole bunch of very rare cases for which it's very hard to get data for. So one approach to that problem is to rebalance your data set by maybe removing examples from the class, which is very popular, and trying to find more data from the rare cases. But that's really hard work. So this is quite exciting because you could hopefully use this technique to generate more examples of, for example, rare cases or cases where you can't find data in volume. However, and there's always a downside, you can't generate diversity. That's the problem. So this is one way to visualize, say you have like a set of data and you want to look at how it spreads out. This is one way to map that variance to a sphere. And if you were to train entirely on a data set with one gender, you won't know how to produce the other gender, for example. So although you can mix and match between parts of your data, you can never explore parts of the data set which you don't understand. However, you can mix styles, and this is one of the other parts of the work that's quite exciting. So on the image here, we've got a bunch of pictures running down the left-hand side, and then we're borrowing image features from the images at the top. So in that first row, we've copied coarse features, so things like the shape of the head or the pose. And then in the next row, we copy kind of features that aren't quite so significant, things like the shape of the mouth or the hairstyle. And in the image below, we just copy really kind of fine-grained features, so textures and colors. So what I hope here is that we can, in future, start to generate data sets which we can control the distribution. So, yes, sure, faces are really useful, but also things like other objects or perhaps scans in medical healthcare. And by being able to select what parts of the image you want to see expressed, you can control how much data you have in each class. And also, this is quite an important technique if you work with faces generally, because as a data type, there's a lot of controls around working on faces. It's very personal data. And also, you need to ensure that data is collected with informed consent. And nowadays, it's more difficult to collect face data. So if you can generate data that's synthetic, that's very useful. OK, so just for you to wrap up here, it is a very broad topic, and I've covered just a small fraction of it. But some of that, I hope, is what is kind of currently of interest in the field. Certainly, deep learning has changed the way that we solve problems in computer vision. So going back 10 years, the way we would do image classification was quite different. And the effect of deep learning, I think, is going to be bigger in the near future. Even for stuff like 3D reconstruction, using deep learning to calculate the disparity will be used. And the kind of work you can do with GANs is incredible, to be honest. In some ways, it's a bit like magic. So there we are. Thank you very much.